Good day, everyone. Today I'm going to go over Module 4B, which is acid-base chemistry and proton transfer. Okay, so the first thing I'm going to go over with you is just general chemistry acid-base definitions. Probably nothing you haven't heard of before, just kind of a review. Then I'll get into acid and base identity and function, which is pretty much the same thing. Just a few examples just to get you back into gear. The dissociation constant, so the acid dissociation constant, and pKa values and their meaning. Coordination and proton transfer, so how a lone pair kind of reaches out and picks up H plus or simple nucleus. Okay, what actually affects the Ka? So we'll get into some subclasses here. Resonance effects, electron withdrawing, electron donating groups, and things like that. Then non-traditional organic examples. So you're going to see some things that are going to be sort of contextualized from what you've learned up to this point structurally. Inductive effects. So whether they have the ability, or some particular functional group has the ability to dump electrons in. Then we're going to look into some ion stability effects, so carbocations and maybe some shifting and rearrangement. Then the second half of this is really going to be more geared towards elementary steps. Okay, so this first half is going to be acid-base, and we're going to move on to unimolecular and bimolecular reactions. So we're going to be looking at substitution mechanisms as well as elimination. Okay, so let's first go kind of take a trip down memory lane here and look at some general chemistry. So per the Bronsted-Lowry definition, a base accepts, so base, let's just say some generic base with a lone pair, okay, sees an acid, okay, so it's going to pick up that H plus, and that acid has the ability to pull these two electrons away and therefore be electronegative, right? So it's going to take its electrons with it. So you can think of that as H plus, no electrons about it, and something else to coordinate in place of what the acid is, okay? So the acid is going to be a donor. Okay, and then this is going to be an H plus acceptor. All right. So generic conjugate acid form is just going to be A plus the acid, and B is just going to be the generic conjugate base form. Okay. So what is the fundamental difference between Bronsted-Lowry and Lewis acid definitions? Well, we're going to be dealing with organic solvents here, so we're going to be dealing with both protic and aprotic solvents, right? So if you wanted to just think of an aprotic solvent, you would think of acetone, so that's aprotic. And something as general and as wide-reaching as some kind of alcohol or water is going to be protic. Okay, so let's go into a little bit more depth in terms of what kind of acids and bases there are. Now we can think of this first equilibrium in your notes here. So this is going to be HCl, which we typically think of as a strong acid. And then we have that in the place of, let's say, NH3. Okay. So this is going to be a weak acid. Sorry, this is going to be a weak base. And this is going to be a strong acid, as you know. Okay, remember that NH3 on that nitrogen has a lone pair to fill up that octet. So in other words, that lone pair can coordinate to that hydrogen, which, remember, if this goes to its conjugate base form, this is going to be Cl minus, right, the conjugate base of HCl. And then you're going to have NH4, which is going to be a charged particle. Okay, so there's some kind of charge separation when you have a proton transfer in this particular instance. Net neutral to start out with. Okay. Now I drew a small arrow here because very little of it is going to exist in this form. It's going to go readily protonated into the other direction. Okay, so if you think of the other equilibria that I asked you to balance out here, we have carbonic acid, which is not as strong of an acid, but still moderate diprotic acid, so that means it has not one but two equivalents of H plus here. And then you have water, which, if you recall, kind of has some basic and acidic properties, right? So it can behave as a base to form typically what you think of as, let's say, picks up this one. I know the connection's not exactly perfect here, but let me redraw this. Okay, so that's an H. It isn't directly attached to the carbon, I know that. But, okay, so just for the sake of simplicity, we form H3O, which in an aqueous system, this would be your H plus, right? So, so then you would have a conjugate base of carbonic acid, which is just going to be a carbonate or a monocarbonate here with hydrogen on the attached to another oxygen. Okay. So this is going to be stabilized because we think of this anion, right? It can actually conjugate just fine, going back and forth and resonate, and have a resonance hybrid, right? So it's going to fluctuate back and forth between these two forms. It doesn't look very different, right? If I were to flip this over and look at it here, it would look the same, but just understand that these electrons basically toggle back and forth, and that negative charge sways back and forth between one oxygen to the next. If this one's lost, then there are even more negative charges that kind of float around and go around the circle there. So it stabilizes everything. Okay, so let's look at one last example. Let's look over on the other side here. So here's sort of a less obvious example here with acetone. Okay, so we don't really think of this being very basic, right? You typically think of something that has an additional lone pair and a charge as something that could pick up some kind of hydrogen. But if there is enough of a strong concentration of acid around, and this is a strong acid, this is going to coordinate, and you're going to get a protonated form. Okay, so remember that if we're thinking of our charges here, so this is going to be an anion or a conjugate base of perchlorate, or in other words, perchlorate. And this is also going to be, not surprisingly, resonance stabilized. So this kind of acid is really strong. This is a type of acid that you would need a particular type of hood for, being that it's very corrosive. So perchloric acid is one of the strongest that you can find out there commercially. Okay, now for a little bit of a conceptual review. What dictates what a strong acid or a weak acid or strong base or weak base is going to be its ability to ionize. So when I say that, I'm saying, let's say conjugate acid is splitting apart. So you have an H plus, an A minus, right? Make this a little bit more accurate, put a lone pair there, right? So in other words, what percentage of this stuff actually dissociates off? So remember that, it takes two to tango. One hydronium ion and then one conjugate base to split apart, and you have equal equivalents. And then you have so much of this percentage that's still in conjugate acid form. So we think of Ka. Ka is going to be equal to our products at the top, right? So our dissociated stuff. H plus, A minus. Okay, so that's going to be all over conjugate acid concentration. Okay, so that's also pretty much just a form of KEQ, if you recall from Gen Chem 2. Okay, so a low Ka is going to say that more conjugate acid is going to be in equilibrium, so that means it's more stubborn to split off and become ionized, right? So unless it has something that's really high in conjugate base concentration, that it has more of affinity to pick up that that hydronium ion, there's really going to be a high probability that it's going to be in a conjugate acid form. Okay. So let's see here. So higher comparative Kas, that means the more dissociation you get. So if you have a very strong acid, you're going to see much higher much higher percentage of things being dissociated. So the lower the pKa, that's going to be the stronger acid. So remember that the pKa, and we're not going to get into all the math, spare you that. So negative log base 10 of Ka is going to be equal to the pKa. And the way you can think of it, at least in, we'll say, aqueous solutions, that pH at which that H plus becomes fully dissociated from A minus, that is what is going to be your pKa. So let's say if you have something like acetic acid, so that has a pKa of around 5, right? Now, if you put that into, let's say, physiological pH, so 7.4, 7.2, somewhere in that neighborhood, that hydrogen is going to be fully dissociated. Okay, so if it's lower than that, let's say if it's about pK or pH of 4, this is going to be fully protonated. Okay. All right. So in other words, when you think about any type of mechanism that we get into in the next few chapters, you really have to think of what kind of environment am I in. Am I going to be under a basic environment where this is going to be higher in concentration, or am I going to see an acidic environment where more positive charge or H plus particles are going to be in higher concentration? Okay, so remember that pKa is going to be logarithmic, right? So for every unit, so this is 10 to the 5 if you were to try to put that backwards. Now, let's think in terms of some of the pKa's that you'll see in your table in the back of your text. So let's go over a couple examples here. This should be in Appendix A. This is at the end of Chapter 26. Something you'd probably want to bookmark, not just for your assignments, but just for in general studying. Very handy little table to have. Okay. So you can see, I'll just do a pretty wide range here. So hydroiodic acid, so HI is going to have a pK of negative 10. Okay, so that's a very, very strong acid. Okay. Trifluoroacetic acid, so if I wanted to have a trifluoro analog of my acetic acid like I have here on the left, that pK is going to be somewhere around 1. Sorry, pK of around 0. Okay, so that means that it's going to be fully dissociated. Or it's going to be near dissociated. Okay. So, but then we get up to really high pK values. And some of these we'll see, we'll say like ethanol. Ethanol is going to be, excuse me, somewhere in the neighborhood of 17. Okay. So in other words, this is a really poor acid. Again, the higher you get up in pKa value, the less acidic it's going to be, right? So the lower in pKa you get, so this is around 5, so this is roughly a weak acid. This is a pretty strong acid. This is a really strong acid. You really have to be careful with HI, right? Okay. So really, if you're thinking about what's a conjugate acid and what's a conjugate base, remember that the acids and the bases are going to be fighting over H+. So if you want a simple analogy, you can think of soccer, right? So let's say some team is from a country where they don't really take soccer very seriously, right? Versus, let's say, somewhere like Germany or like Brazil or just renowned squads that typically win the World Cup, right? Or Argentina or something like that, or Spain. All of those, or even France, whatever. All these different squads, they dominate, right? So if they're very dominant, they're going to behave as the base. They're going to have control of that ball most of the time, right? As opposed to, let's say this team that's out of, I don't know, I don't want to trash any, nationalities, as I understand that people take soccer very serious all around the world. But let's just say some country that doesn't perform particularly well in the World Cup, doesn't make it past the qualifying rounds, etc. They're going to be the acid, right? They're going to be the one that's going to give up the ball and give it to the one that are going to take control and score goals on them all day long. Okay. Okay, so we'll get into some sort of structural considerations as to why things will have low pKa's, high pKa's, and things like that. Okay, so now we're going to get into proton transfer. All right, so we have our acid here on the left. We have our base, a weak base on the right. This is methylamine. If any of you remember from Breaking Bad, the time when they try to stall that train so they can siphon out all the methylamine or get it from whatever that corporation was. This is what it is. Okay, so this is going to behave as a weak base. So it's going to take up that H plus, and then you're going to have these electrons shift over to where this electronegative oxygen is. Okay, so as a result, you're going to get an acetate anion, and then you're also going to have a protonated form of methylamine. So a methylammonium ion, essentially. Okay, so these charges are going to stabilize one another. One other thing just to note about proton transfer in general, since we're going to be dealing with multi-step mechanisms, you have to first think about what kind of proton transfer can occur first, because that is going to be the fastest step in anything that happens. Okay, so that's really important to think about. So the pKa of ammonium or methylammonium here is going to be about 10. Okay, and then for acetic acid, it's going to be about 5. Okay. So in other words, the conjugate acid form that's going to have the higher pKa is the one that's going to end up with the proton, right? So this is the proton that's going to be transferred, and there it is right there. Okay, so let's see if we have another type of base. So we have dimethylamine. Dimethylamine. So that means 2 methyl groups. Okay. And then we have water, which is going to act as an acid. Okay. So coordination step, these lone pair from this disubstituted amine is going to pick up that hydrogen, and then you're going to have OH minus. Okay. And then stabilize that negative charge, you're going to have this quaternary nitrogen here, or quaternary amine, what have you. Okay, so that's a positive charge there. Now, if we want to think of pKa's, this is going to be about around 11. Okay, and then the pKa of this is going to be around 16. Okay, so the difference here is 5-fold, right? Or 5 pKa units. So what does that mean necessarily? That means that OH is a stronger base than dimethylamine. Okay, meaning that if it's a difference of pKa of 5, or delta pKa, that means that OH is more likely to keep that hydrogen by a factor of 10 to the 5. So 10 to the 5 going in this direction. Okay. Now I just kind of simplified these numbers. It's not exactly what's reflected in your notes there, but it's somewhere close, right? So it's a difference of, so the delta pKa is going to be 5. Right? So in other words, it's going to go into the direction where there's a higher pKa value for that particular conjugate acid. So a conjugate acid of OH minus picking up one of these hydrogens to be more abundant as water on this side. Okay. One thing you got to understand about ammonia or some kind of amine picking up a hydrogen and acting as a weak base. Remember, if it's a weak base, conversely, wearing the shoe on the other foot, that is going to be a weak acid as well. Okay, so if that's the case, then see how that positive charge is right there. And this had a pKa of around 11 as opposed to just methylamine that had a pKa of about 10. So it has a tenfold, in other words, ability to pick up a hydrogen and be 10 times more basic. Why? Well, because you're going to form a positively charged ion, right? But these methyl groups, instead of just having one, you're going to have two that are going to stabilize that positive charge. Remember that, because that's going to be important when we start thinking about carbocation stability, which we'll get into later. Okay, so what affects the Ka? Well, everything from resonance, like I said before, also electronegativity, right? So if something's very electronegative, it wants to keep its electrons. So typically you think of something that's like oxygen or like nitrogen that holds these hydrogens, oh right, you know, but at the same time it can kind of go either way and dump them off too. Okay, so you can take a look at some of these examples that are in the back of your text in Appendix A again, and just kind of look at some of the trends where you see where the pK gets lower to higher to higher to higher. Okay, and as you get higher to higher to higher, you see that those hydrogens are actually attached to more electropositive nuclei, like carbon, like nitrogen, etc. Okay? But whatever is surrounding all of that is what's going to stabilize everything. Or destabilize it. Okay, so now we're going to talk about the reason why you'll see some of these pKa differences in analogous compounds. And this really mostly comes down to electron withdrawal as well, or in other words, electronegativity. So you can see iodine is right here attached and 3 fluorines attached. Okay, but what we really want to think about is what kind of anion we'll have as a result once this H splits, right? So we have the conjugate base form here below. Right? We already know that this can resonate back and forth. We have no trouble with that. However, we have this methyl group right here. Okay, so that is really the business end on these 3 molecules is, pretty much apples to apples comparison. However, what the functionality that's beside it really can make a difference. Okay, so we see how that's 1.5 fold or 15 times more acidic than just acetic acid, and then this is what 4.5, so almost 10,000 times more acidic than acetic acid as trifluoroacetic acid. The reason being is that this methyl group right here is actually going to feed electrons in, right? So if we were thinking about our dipole here, it's going to go in the direction of that business end, all right? Now we have, let's say, the conjugate base form of iodoacetic acid. Okay, so we have a little bit of a fight here in terms of polarity, right? So in other words, if this iodine, which is slightly electronegative, is pulling some electron density away from this sort of seesaw of electrons or a negative charge here, that means that it's slightly stabilizing that ion a little bit more, okay? Now, if there's already a negative charge here, conversely on the acetic acid or the acetate form, we have to think that, okay, we're already good here in terms of electrons. So adding more, it's almost like, going for your 5th run at the buffet. It's like, yay, cut me off, I'm good, right? So think about now this trifluoroacetate. Okay, so fluorine's most electronegative of anything on the periodic table, at least that we know of. So that means it's going to pull that negative charge further back, so that's going to stabilize it even more. Okay, so in other words, if you have something to kind of pull and distribute that electron density around the molecule, the more stabilized it's going to be. If you were to try to push more electrons into where that business end is, the less stable that ion is going to be. It's all about ion stability. Okay. Now, speaking of ion stability, we're going to get into resonance effects. So let's think of a nitrate. So, as if you recall from your Chem 1, remember that all nitrates are going to be soluble in water, no matter what they are amended to. And then we also have positive charge here. So this is going to be a net negative anion. Okay. But it's going to be stabilized from these negative charges basically jumping from one oxygen to the next. This nitrogen is going to be positively charged all the time. So this is what is referred to as a zwitterion when it actually has its conjugate acid form, as you know, is nitric acid. Okay, so nitric acid has HNO3. So say if you add an H plus to what you have right here, you're going to get HNO3, and that pKa is negative 1.4. So if it's in the negatives like that, -1, that means it's a strong acid. Things are going to be fully dissociated. The H plus has gone elsewhere. Okay. So again, this is going to stabilize that this net negative charge is going to be stabilized via resonance. So you're going to have, a constant cycle of electrons going around. Okay, so let's say we have something like an amide. Okay, so I'll just put R for a generic alkyl group. We'll have a primary amide. Okay, and now we're going to use nitric acid as a strong acid. We're going to use that amide amine portion of the amide there to pick up a hydrogen. Okay, so we're going to have a conjugate acid form. But if we have a conjugate acid form here, that's going to create an issue. Maybe not one that's readily apparent, but okay, so we have our charge separation here. We have two neutral compounds or species here, left and right, and then we have positive and negative here. Okay, so when this picks up a positive charge, remember that lone pair can actually resonate within this double bond here. So there can be a swing and charge separation with that carbonyl. So in other words, you need a really strong acid to sort of disrupt that that resonance. In other words, this is going to be a really poor base because you have not just resonance here, but you have an electron withdrawing group right nearby. So that positive charge is going to be very destabilized by an electronegative moiety that's going to pull electron density away. Okay, so in other words, if you already have a deficiency in positive charge or in electrons, it's going to be further pushed by an electron withdrawing group like a CO double bond. Okay, so just a little bit of a shorthand disclaimer here before we get started. This pH that I'm going to write down below is just going to be representative of these phenyl groups that you see right here. Okay, so this OH minus anion is going to pick up this hydrogen. Okay, so this is effectively going to be working as an acid. So this is a, think of this as sort of not a very good acid, right? Because it has a pK of 9. But lone pairs, or these two covalent bond electrons are going to swing up to satisfy the octet of this carbon and this carbon here, and this pi bond is going to kick out, and then you're going to have a negative charge up at that oxygen. Okay. All right, pH again to shorthand the ring. So what you see here is pretty much an sp2 environment throughout. So that's good. That means everything's stable and everything's going to a negative charge can resonate back and forth by pushing electrons down, right? So do-si-do back and forth, but you also have these electronegative phenyl groups that are going to be pulling some electron density away too. So that's really what you're going to see in terms of a difference here between pK of a 9 and pK of 13.3. So you have some aliphatic methyl groups on the wing there on both sides. So in other words, you're still going to have the same resonance structures, albeit they will not have that electron withdrawing effect that you have from those two rings. Remember that rings can also resonate with everything if everything's in an sp2 construct like you see. Okay, so this is going to be sp2 hybridization throughout. Okay, so again, OH is going to behave as a good base. Why? Because the conjugate acid form, remember, water is going to be about 15.7. So if it's 15.7, that's higher than 13.3, higher than 9. So that, in other words, OH is going to be a stronger base than this, conjugate base form of this diphenyl dione. 1,3-diphenyl, 1,3 propane dione compound. Okay. So in other words, it's going to be a stronger acid than this is going to be, right? If you want to look at it from the other side, another angle. Also take into consideration, once you pluck that hydrogen off, you have a negative charge following, right? So in other words, you always want to follow your charges in organic chemistry, especially if you're talking about mechanisms here. So if you're, if one thing's charged and the other's not, I understand you're going to be dealing with A, B, C, D questions, etc. But in other words, you really need to understand what's going on mechanistically, or you're going to get lost pretty quick. Okay, so this is going to be able to resonate back and forth. Okay. So in other words, the ketone shifts to one side to the other. Okay. And that negative charge goes to the other side. Okay. Same thing with this. Remember that for resonance forms, you have that double-ended arrow. Sorry, cramped everything together there. Okay, but should be a good general representation. Okay, so again, these methyl groups are going to feed some electron density in here. That's not a very good move when you have a negative charge and you're already at a capacity, if you will. So in other words, this is going to be a more stable anion than its methyl counterpart at the right. Okay, so speaking of inductive effects, let's get into those. Okay, so let's go over some inductive effects. Now, so you can break up groups into two different categories. One being electron donating, so in other words, it can push some electron density in, or electron withdrawing, so it means it pulls electron density away. So the first example that we have here is again just going to be some generic alkyl group. An alkyl group itself is going to be electron donating. Okay. Just remember that carbons are going to be sort of on the slightly electronegative slide, but remember that we're dealing with organic chemistry, so everything is going to be carbon-based. So in other words, it's going to be no man's land. We're really going to see that when we get into carbocations and carbanions. Okay, but first, let's learn to crawl before we walk here. This chloro group is going to pull electron density away, so it's going to destabilize a positive charge, it's going to destabilize something that's be positively charged around it, but stabilize something that is negatively charged around it. So you can think of it the same way that we saw some of the other halo groups that were attached to an acetate anion. Okay. Now a methyl group. Again, that's going to be electron donating, so it's going to push electrons inward. So it's just something that's more electronegative. Okay, so in other words, this would destabilize a negative charge and stabilize a positive charge. Positive charge means that it needs more electrons. Okay, so that would be the inductive effect going into something that would positive. Okay, so this is an electron withdrawing group, this chlorine. So notice that EWG stands for electron withdrawing. This is going to be an electron donating group, ever so weakly. OH. Okay, so we have a lone pair here, and we think of oxygen as electronegative, so it's that electron hog. It wants to keep its electrons. However, it has no problem kind of lending a pair out, bumming it, as long as it gets it back, right? So think of it like a payday lender, right? It'll give it to you, no problem, but it wants its money right back in full effect. So we think of this R group, let's say it being negatively charged. That electron donating group is going to be not so welcome, right? But it could resonate with something else, right? It can't really resonate here if it has that hydrogen that's attached. So remember that oxygen already has a full octet in this particular case. But on a positive charge, it would be definitely stabilizing, right? So it would destabilize the negative charge, stabilize a positive charge. Okay, so you might have seen this already with some of your resonance structures that you've worked out elsewhere in this course up to this point. So this can stabilize a nearby positive charge just via resonance. Okay, so this is electron donating. Okay, that phenyl group is going to be slightly electron withdrawing. So it's going to slightly destabilize a negative charge and stabilize a positive charge. Okay. Also think of the phenyl ring as being able to basically have electrons whiz about at a very high speed. You'll have an electric current there about that phenyl ring. Okay, so this is an slightly wet electron withdrawing, and then finally we have this sulfonate or sulfonyl group. This is going to be electron withdrawing. You have 4 oxygens that are attached to that sulfur. Sulfur itself is not very electronegative, but those oxygens sure are, boy. Right? And then it can also resonate if it drops that hydrogen, right? So chances are something is going to be a little bit more basic than that, and it's going to scoop that hydrogen right up. Okay? So this is very much electron withdrawing. And would stabilize a negative charge and highly destabilize a positive charge. Okay, so let's think about carbocations and then carbanions. So carbocations, let's just say this methyl carbocation here is going to be stable or destable, or unstable, sorry. if you have a hydrogen here, hydrogen is really sort of like the no man's land of electronegativity, right? It's neither nor. So in other words, it doesn't really have a lot of electrons to throw in and not really anything to take out, right? Because there's only a duet around hydrogen anyway. So in other words, this is going to be the most destable or unstable. Wow, if I speak today. Carbocation. Okay, so this is carbocations. Okay, so that plus charge is going to be about the carbon. Okay, so next is going to be a primary carbocation. So that's one with a degree sign. That is simply going to be slightly more stable just because you have this one electron donating group that's going to stabilize that positive charge. What geometry is this particular carbon going to be in? It's going to be sp2, all right, because you have two coordinates from the hydrogens, each hydrogen here, and then one coordinate from that methyl group. Okay. So the next one up is going to be secondary. So that's second most stabilized. And as you might guess, if you have a tertiary carbocation, that is going to be most stable. It's going to be particularly important when we think about charge stability in particular solvents, namely protic solvents. Okay, so that positive charge is stabilized by these three methyl groups feeding electron density into where that electron deficiency is most needed. Okay. And then we have carbanions, which you might have guessed actually follows the opposite trend. Okay. So to have a full octet about carbon here, this does not have a full octet, by the way, so that's another reason why these are very much intermediates. These are not things that you can pick up out of a bottle, something I might want to mention to you. Okay, so neither of these really, unless they have a very stabilized charged, counter charge to them. Okay, so this particular carbanion is going to be most stable because, again, it's already good in terms of having that negative charge. It doesn't need any more electrons from something else, right? So any other methyl groups that you tack onto there. So if you do tack on your first one, it's going to be less stable than what you see there in the methyl form. Okay. So in other words, tertiary carbanions are definitely a tough sell. Okay, and then what are these hybridizations or geometries going to be? So this, for carbocation geometries, that's going to be trigonal planar. For this, it's going to be different. Remember that if you have a lone pair, it's going to distort the geometry a little bit, and it's not going to be quite tetrahedral. It's going to be more trigonal pyramidal. Sort of like you would think of with let's say NH3. Okay, so here's the least stable form of a carbanion. Okay, so just to rip through some of the concepts to kind of guide you along with acid-base chemistry here, or at least within the context of organic chemistry, is to think of course, the charge, right? where that charge is going to appear, if it's going to be on a carbon, if it's going to be on an oxygen, nitrogen, etc. So if it's an electronegative one, then you know, more likely to see a negative charge. What else is surrounding it? Okay, so we're thinking about delocalization or resonance. Okay, so resonance is going to be about an sp2 construct. Okay, so the more resonance forms you can have, of course, the more stable that particular anion, cation, whatever is going to be. Okay, and then the last is going to be the inductive effects. So in other words, electron withdrawing groups or electron donating groups, and whatever charge they're stabilizing. Okay, so whether it's a positive or negative charge to stabilize. So the electron withdrawing group is going to stabilize a negative charge. Electron donating group is going to stabilize a positive charge. So a donor, we'll say for something that's positively charged, again, you have to think in terms of electrons. It's all about electrons and electron density. Okay? Okay, so to kind of dip your toes into mechanistic or mechanisms in this course, which is really kind of the meat and potatoes of this particular course, Organic 2 is really going to be more of synthetic strategy and spectroscopy. But again, you kind of need to know the ins and outs, right? So it's sort of like driving. You want to know how to reverse, you want to know how to drive forward, you want to know how to turn, you want to know how to shift gears, right? So elementary steps, it's not to say that you're counting your, 1, 2, 3s or working with your ABCs. We're working more along the lines of what is going to coordinate to one thing or what is going to be coordinated. So we have electron rich and we have electron poor species. Electron rich is going to be a nucleophile. So you'll see this sort of shorthanded as NUC with sort of a colon right there. Negative charge usually, or have a partial negative. So you have like a delta sign there, right? It's going to be negative. That is if you have some kind of dipole. So something that's going to be negatively charged or have some net dipole is going to be a nucleophile. Now, conversely, an electrophile is something that's going to either be positively charged or have a partial positive charge. Again, delta. It's not the world's best delta, but a delta positive charge. So in other words, typically some kind of carbon, right, that's going to be electron deficient from something pulling electrons away. Let's say like an electron withdrawing group, right? Now, we always want to have a balance of charges, right? So even if we have a negatively charged nucleophile, there's going to be some positive charge to sort of balance it out. So if we think of a Grignard reagent, which is something you'll get beat over the head with next semester. So remember I was talking about a carbanion like CH3 minus, which is going to be stable. Okay, you need to have some kind of stabilized charge with that. So in other words, let's say you have MgBr. Now magnesium, if you look in your periodic table, it's going to be right there in group 2A, so that means when it's charged, it's going to be 2 plus charge. Okay, so remember that bromine, since it's going to be in group 7A, it's going to be a -1 charge. There's a -1 charge here, so in other words, it's going to be stabilized by this net positive charge. Okay, now this is going to act as a very aggressive nucleophile, right? And it's going to coordinate to something that is positively charged. So let's say we take the world's most simple electrophile, and that would be H+. So if we have some coordination right there, voila, we have CH4. Okay, so really we haven't seen anything different from that. Let's say we just use, in place of this, an OH-. Now, it wouldn't be paired up with this magnesium bromide that you see here. It would be, or that positive charge would be, combined with, let's say, sodium plus or potassium plus or something like that. So you generate methane, okay, from this picking up an H plus from some kind of acid, right? So it's never in free form. It's always attached to something. It would be its, conjugate base. Okay, so this would be a proton transfer. Again, that H plus could be an electrophile, but let's think about something that's a little bit more elaborate than that. Okay, so, but before we get into more sort of detailed mechanisms here, let's look at what goes from in terms of flow of electrons. So notice how we're going with nucleophile going to the electrophile. So that's what you're always going to see. So let's say we have something that's not such a great nucleophile. Okay, this is ethanol. Not the world's best nucleophile by any stretch of imagination. It's actually kind of weak. Okay, and we'll get into what constitutes a weak nucleophile versus a strong one. A strong one is going to be less stable. Again, something that's going to be charged, where something poor is going to be, nice and happy and doesn't have any type of charge to it. Now, if we think of a dipole, we think of a dipole going in this direction, right? Because that oxygen is most electronegative. Okay, and then there's some inductive effect from these this ethyl group right here. So it's going to push some electrons over in that direction. Okay, so that means we're going to have partial negative at this end, partial positive over here. Let's say we have propyl chloride. Okay. This chloro group is going to be pulling electron density away from this carbon in particular, because it's closest to that chlorine, so that means it's most attached, and that means this bond's going to be a little bit more stretched from that dipole. Okay, a little bit of a segue into what we're going to be looking at in the next couple chapters. Remember that a dipole moment is going to be stretched with an aprotic polar solvent. Okay. Now back to our partial negative, partial positive charges here. We have a partial negative over here where this oxygen is, partial positive where this carbon is. So that means that these lone pair actually want to coordinate to where that partial positive is. Think of it almost the same way you think of dipole-dipole interactions, right? But now you have some coordination and, electron surplus to electron deficiency. It's always going to go in that direction. It's never going to go reverse. Okay. So either partial or full positive charge to from a full negative charge going to a full positive charge. Electrons coordinating, that is. Okay, so if you have things that are coordinating and it's happening at a very fast rate. Now, we haven't really talked very much about kinetics just yet, but let's say we have a very much more powerful nuke, sort of like we had up at the top here. Right? We have just some generic representation of some tetrahedral complex. Okay. So I'm going to put LG right here. That's supposed to denote that that's a leaving group. So LG equals a leaving group. All right. Sorry, we can't see that. Pull this up. There we go. Okay. Now, now this nucleophile, again, this is going to be the species that coordinates. It's going to go right there to where, let's say this particular leaving group is going to be electronegative. It's going to pull electron density away from that particular carbon. We can just pretend these are hydrogens or carbons that are directly attached to that center right there. Okay, so we have some kind of intermediate. Okay. So something's coming, something's going. Nuke's coming in, leaving group's gots to go. Okay. So you'll see this delta G double dagger that you see right there. That's just to denote that that is what is referred to as a transition state. Now, if the nucleophile isn't as good of a nuke as if it, let's say if it's better off as a leaving group, and this is better as a nucleophile, again, you don't really know, right, just yet. We haven't really determined what's a good nucleophile and what's a good leaving group. But just for the general sort of theory here, just pay attention to the idea that it's going to take two to tango. You're going to need the nucleophile, right, or NUC, and then you're also going to need the electrophile, or what is referred to as your substrate. Right. Okay, so now we're going to go over just some basics in terms of bimolecular mechanisms. So bimolecular meaning that both concentrations, notice how I have everything in brackets here, are going to be dependent upon in terms of how fast or slow the reactions go. So in chemistry, it's not a matter of when or if, it's more of a matter of when, right? So, of course, if it's a bimolecular mechanism versus a unimolecular mechanism, things tend to go much faster, okay? Now, with that said, if things are kinetically forming, right, as opposed to thermodynamics, that means that it's going to go to, that product the fastest. It may not be most thermodynamically stable, but it's going to lead to that product much quicker. Okay. Now, the first step, first instance we'll go over here is substitution. So SN2, this 2 means that it's going to be bimolecular, but things are all going to be happening in one step. Okay, so that lone pair from the nuke is going to be coordinating and kicking off this leaving group all in one fell swoop. So that transition state that I showed you before is something that's just almost like a freeze frame, right? Or a still capture of what's going on here. So A, B, C, again, those are just generic forms. I could really put sort of quotation marks, if you will, beside each one. Okay, but that leaving group is going to go and it's going to take that electron, those electrons with it, okay? All right, so it's going to be some kind of stable anion that's going to rest there, and it's going to leave, right? So in other words, whatever the positive charge here that was stabilizing this particular nucleophile is probably going to stabilize that leaving group. Okay, so as a result, you're going to have the nuke that is substituted what that leaving group was attached to the electrophile. All right, so what that means is that it's substituted this leaving group. It's become a more aggressive, more stabilizing complex with that substitution. Now, we're going to see some instances where a nucleophile can actually behave just as much as a leaving group and vice versa. So, kind of just take this for what it's worth right now with just a generic approach, and we'll kind of hash what will push one off, one species off versus the other. Okay. Now, conversely, let's think about elimination now. So this is a different type of mechanism. So eliminations tend to occur at higher temperatures in that they actually form an additional species from what you started off with. So notice that both of these have a leaving group. Both mechanisms have a leaving group. So that's very important. Both are bimolecular, as you see right here. So you have two different components that are concentration dependent. Again, the brackets are going to give you the indication that the concentration's there and it's relevant. This is not typically how you would write mechanisms, just FYI. I'm just trying to give you guys the sort of crash course representation here. But a base is going to take this hydrogen that's attached to this alpha carbon relative to where the leaving group is, okay? Or where the leaving group is attached, rather. Because that leaving group is going to be electronegative, and it's going to pull these electrons down in this particular direction. Now, if we're thinking about things from a three-dimensional perspective, that hydrogen and that leaving group are going to be anti to one another, okay? So they're going to be in the same sort of spot right here if we were to turn this around 90 degrees and put it in front of you. Okay, so when this hydrogen is stripped off, these electrons basically just cascade down and kick off that leaving group. Okay, so once again the leaving group goes. Okay, and then you're going to have, again, you're going to have that negative charge there. So the negative charge is conserved throughout. So now you're going to have an alkene as a product, as opposed to just, I'm going to put that as alpha just to sort of earmark it. Okay. And then we'll have D and E here. Okay, reason why I skip C is because you may confuse it for another carbon, right? Okay, so essentially you're going to form an alkene group from an elimination. You're eliminating this hydrogen and this particular leaving group, taking it off, and then in its place will be a double bond. Okay, so not only do you have that alkene group, but you also have conjugate acid of the base. So we'll just put B and H. So in total, and think about this later when we get into high temperature versus low temperature, these are going to be a low temperature. This is going to be a high temperature. Reason being is because temperature drives entropy, right? It creates more disorder. So, in other words, you're starting off with two components, you're ending up with 1, 2, 3 components. So that's just sort of a thermodynamic, qualitative way of looking at things. Okay, so let's go over a couple of other mechanisms that we won't necessarily focus upon in the next few chapters, but further down the line in organic chemistry you'll encounter. First is electrophilic addition. So in this case, you're going to have a particular alkene that is going to behave now as a nucleophile. Okay, so it's going to react with some kind of acid, strong acid. Okay, so in other words, it's going to behave as a base, really. And then a positive charge is going to be there. Notice how it's going to be at the most substituted carbon, so it's going to be most stable. And then that conjugate base, A minus, is going to coordinate there, the positive site, and then you'll have your electrophilic addition. Okay, so the electrophile in this case is just going to be hydrogen, something that's may have a partial positive or a fully positive charge. Okay, so this is going to be the substituted form, or sorry, the addition form. So whatever that conjugate acid is, it's going to amend there at the most substituted carbon. Now, the next is going to be a nucleophilic addition. So you might see some examples in your text here. Let's just take that Grignard reagent like what we had before. And then we have, let's say, some kind of a ketone, or sorry, aldehyde here, rather. Okay, so just like some of the leaving groups we saw before, this oxygen is going to be electronegative, and more bond orders that you have, the more electronegative that particular moiety of a species is. Okay, so this negative charge is going to attack where this partial positive charge is here, where this carbon is, so it's going to be electron deficient from, again, electrons going up. So we're going to go from an sp2 to an sp3 intermediate. Okay, so we'll have that hydrogen there. CH3 here, CH3 here. Okay, so that is a nucleophilic addition. Okay, and then the third, which you'll encounter next semester, is going to be a nucleophilic addition / elimination. So you're going to have this tetrahedral complex, but you're also going to have some leaving group. Okay, so let's say we have an ester instead of an aldehyde like we have here. Okay, so that's OCH3, just to denote that it's a methoxy group. Okay. All right, and then just like before, have this attack, kick these electrons up. We're going to have some tetrahedral intermediate. And based on everything that's here, the species that is most likely to leave and have a stable negative charge is actually going to be that OCH3. Not the world's best leaving group, but it's a better leaving group than a CH3, which is going to stabilize that carbon there a little bit more. So you will have a acetone product. Okay, so let's now think of carbocation stability and see what kind of rearrangements we can come up with here to make something more stable. Now we have 1, 2, 3 different secondary carbocations. Remember that it's not the most stable carbocation that you can form. However, we're going to see that there are going to be some exceptions that you're going to see. Okay, so the first one here, so this is a secondary carbocation right there where that C is indicated. So we want to have something that's by default more stable, so we could have this hydrogen right here perform what is referred to as a hydride shift. So in other words, it's going to take those electrons with it, kind of work that orbital over to where this carbon is and have a deficiency at this now tertiary carbocation. So what you would do mechanistically, just with an arrow, is go in this direction. Make sure that your arrows, by the way, are double, or sort of in an arrow form, not in a single sort of fish hook designation. That's the difference between that is 2. If it's the head is 2, that means that there are 2 electrons that are going. If there's just 1, that means there's just 1 electron migration, which is radical mechanisms, which we'll get into in chapter 25, way at the end of the course. Okay, so this is a hydride shift. So I'll just have a little tilde sign with a H beside it. That's to indicate that a hydride, so that means a negative hydrogen has moved over to satisfy that positive charge and establish a full octet about that carbon. Now we have, I'm just going to write the 2 hydrogens there. With that positive charge now on a tertiary carbocation that's more stable. It's going to be further stabilized by resonance, right? Because we have that lone pair about that oxygen of that alcohol group, and that can kind of shift back and forth and be a resonance contributor. Well, if that's the case, this is actually going to be a more stable resonance form, because there's going to be, remember, you still have those 2 electrons that are still attached to that oxygen, or orbiting about that oxygen. So there's going to be 1, 2, 3, 4, 5, 6, 7, 8 electrons surrounding that oxygen. There's going to be 8 electrons surrounding that carbon too. So this is going to be the resonance, major resonance contributor. Okay. Now, again, this positive charge is where a nucleophile would come in and amend to. Okay, not at the oxygen. Okay. Now, apologize for the sirens. This isn't normal. Now we have another secondary carbocation, but notice how we have a quaternary carbon right next to it. So in other words, that carbon is fully substituted without any hydrogens. This just has 1 hydrogen. Remember, this is going to be sp2 in geometry, or in hybridization. Now this is going to be a little bit different of a scenario, because this is going to be a methyl shift. So that CH3 minus is now going to shift over to stabilize that charge, and the charge is going to migrate up to where that methyl group was once branched and attached. Okay, so what I would do is draw this tilde sign with CH3 right there. That's going to indicate in shorthand a methyl shift. Okay, so this is all going to be important when you think about unimolecular mechanisms. Things aren't going to be as straightforward as what we saw earlier with bimolecular mechanisms. Okay, so now we have methyls in a 1-2 relationship about that cyclohexane ring. We have that positive charge. Sorry, the positive charge has moved up. Not like it matters. It's still disubstituted. Okay, so, but we want to make sure that that migration of charge is shifted over there to a more stable tertiary as opposed to secondary there on the left. There's no resonance forms or resonance contributors here because there's no lone pairs that can feed into the sp2 carbon. Okay, last one here, which is kind of a giveaway. This is a secondary carbocation, but it is resonance stabilized by this phenyl group. So I'm sure you might have looked at this and think, oh, well, I bet this methyl group is just going to shift over and you could have a tertiary carbocation here. Well, that could be the case. you can see a little bit of this transfer occur. But remember that that positive charge is going to be more stabilized by some kind of resonance form. Okay. Okay, so this is from a methyl shift. Okay, so the last thing we're going to cover in this module is keto-enol tautomerism, or submodule rather. Okay, so keto form is going to be what the name suggests, is a ketone, right? So let's say we just have two butanone or butane 2-one, whatever. Okay, we have this in the presence of water. Okay, so some kind of protic solvent is going to be here. And remember, if we're thinking about acidity here, because this is going to be a very poor acid to protonate that oxygen up at the top there of that ketone, we're going to think of what is the most thermodynamically stable ion that you could form. Now, if you think about trends in terms of alkene stability, the more groups that you have attached to them in place of hydrogen, the more stable they're going to be. So if you were to deprotonate from this methyl group, if you had a strong enough base, you could do so, and you'll see that later on in the course. But if you take it from a carbon that is more substituted, so this is terminal methyl here, this is a methylene group. So it has not just that carbonyl, but also that methyl there. So with that carbonyl is going to make this more acidic, right? Because either of these carbons more acidic, or hydrogens where these carbons are attached more acidic rather, because this is electron withdrawing, right? And what are you going to have as a result? You're going to have a negative charge for a conjugate base, right? So you'll have these electrons that come up Okay, so first thing you'll have here is H3O, which is positively charged, right? And then you're going to have a negatively charged keto form, okay? And this can actually resonate. And kick this double bond off, or pi bond off. Okay. All right, and then you're going to have this enolate, okay? Now, this is going to behave as somewhat of a nuke and take the hydrogen away from this hydronium ion, right? So it does. I mean, it's goodbye to both of the charges, and then you have water plus your enol form. So we have keto on the left here and enol on the right. Okay, so if we were to draw, let's say, equilibrium symbol between the two. This is going to be really small going in the enol direction and really great going in the keto direction. Reason being is that this is highly favored relative to the enol form. And the reason being is because the sum of all the bonds that you see here is going to be a higher energy than the amount to break the bonds that are over here. Okay, so a CC double bond and a CO double bond, if you go back to your first chapter tables, you'll see that they are not equivalent, right? There is going to be a higher bond energy among the CO as opposed to the CC. And, you see the net sum of it being slightly greater for the keto form. So you're going to see this in, north of 99% abundance. So this will be, a decimal point of a percentage of abundance here for the enol form. Okay. Now that's if you actually have a protic solvent to where you can actually facilitate this proton transfer, right? So in other words, water is acting first as a base, and then on the second end step, it's acting as an acid, right? So if you don't have something that's protic, that's really going to kind of make this much more difficult. And if you had something you started out with as in an enol form, it might just stay that way. Just a little bit of a hint for you on an exam question, maybe. Okay, so you can see how some of the base catalyzed versus acid catalyzed mechanisms work in your notes here that I've given to you already. You can pretty much just see this happen in a more rapid fashion. Now, water isn't the world's greatest base, right? So for it to take this hydrogen off is going to be kind of a tough sell. Now, you were to acidify, or if you were to use this under acidic conditions, that oxygen is going to get protonated, and therefore, if it's going to be positively charged, it's going to draw electrons up, right? A base, if it's under basic conditions, it's going to strip this hydrogen off more readily, okay? So you're going to be following a positive charge on acid catalyzed, and you're going to be forming a negative charge on a base, you're going to be following a negative charge on a base catalyzed reaction. Okay. Now notice here how everything was kind of net neutral going from one step to the next. That's because this is all under neutral conditions. There's no abundance of OH or H+. Okay, so it's neither nor. A base or acid catalyzed won't really, tell you which direction things are going to go. These things can work in reverse too. Remember, you can always. That's why I was trying to say this is sort of like driving a car with mechanisms. You can go forward or you can go backwards, right? All right, so that pretty much sums it up for elementary mechanisms. The next module or the next part of this module is going to be very detail oriented, so spend as much time as you can working out some examples. Come see me during office hours. I'll have some extra examples to work out for you. Okay, everybody have a good one.